The material that we're going to look at today is going to apply to non-right triangles. And so overall, or like as a group, if you see the word oblique, oblique means non-right. Okay? So an oblique triangle is a non-right triangle. So an acute triangle or an obtuse triangle is oblique. Okay? If you are working with right triangles, then using trig ratios and Pythagorean theorem tends to be the strategy that you will apply. Okay? And so the things that we're going to talk about here today have to do with non-right triangles. Okay? Starting with an area formula. Okay? We're also going to be talking today in this section about some of the congruence patterns for triangles. If you recall those, we have SSS and SAS. Those are the triangle congruence patterns that involve two sides. And then we have ASA and AAS. Those are the congruence patterns for triangles that involve two angles. So those are the categories that we're going to kind of distinguish as we go through the couple different things from today. Okay, so the first thing is the SAS pattern, again, recognizing what you have. So if you have a pattern where you have two sides and the angle in between them. So let's say side B, side C, and angle A, if we were looking at this example here. So side B, side C, and angle A. If this was the measurements that you actually had, you can find an area formula for that. And I'm going to derive it first, and then I'll show you the different versions of it. But if you took this triangle ABC, and the area formula was 1/2 base times height, where our base is one of these sides, right? So we have 1/2 the base B, and then this is our height. This corresponding height, I'll draw that in as an H. Okay, in looking at this, what we create now is this triangle here, this right triangle, where you have your known angle A, H is opposite that known angle, is a leg opposite, and C is the hypotenuse of that right triangle. So if you took opposite and hypotenuse, which trig ratio relates those two elements? So, right? So what we could do is we could say that the sine of angle A is equal to, in this right triangle right here, is equal to opposite H over hypotenuse C, which means we actually have an expression for the height. If we multiply both sides by C here, we get that the height can be calculated using the given information as C times the sine of A. So if we substitute that height in right here, C times the sine of A, this gives us our area formula for that triangle. It's 1/2 the product of the two given sides, B times C, all times the sine of the angle between those two given sides. Okay? And so this is the formula for area given the pattern SAS. Now, there's two sort of alternate versions of this depending on which sides you were given. Okay, so you could also have said that if you were given sides A and C and angle B as your SAS pattern, then you would take 1/2 times the product of the given sides A and C times the sine of the angle between those, between A and C is angle B. And then the last possible combination here is if you were given sides A and B and angle C, the included angle there, you could take 1/2 times the product of those given sides, A and B, times the sine of the angle between that, which would be C. So all of these sort of apply to that first highlighted formula, but it all just depends on which pieces of information are provided. And so I want you to see if you can apply this formula here to the first question. Okay, on this one, do change C from 30 to 3. So use 3 as your side length C. Okay, and then go in and see, can you determine what the area of that triangle would be, please? All right, so if you're comfortable with this pattern, you see it, your pattern you recognize, SAS. So you have an area formula for that. The area formula is 1/2 the product of the two given sides. So here's your two given sides, 3 and 7. Times the cosine, or sorry, times the sine of the angle that's between them, which is 60 degrees. And so if we are calculating this, we can enter our answers. Now, if you are going to use this Desmos calculator, again, open it up, always double check the settings, make sure it's in degree mode. So notice I'm in radians. Since I'm going to be using trig ratios, I want to make sure I'm in degree mode. And so then I can calculate 1/2, 3 times 7 times the sine of 60 And there's my answer, 9.093 for my answer. Now remember, we could also enter our answer on my open math as a calculation. The only thing to make sure of in that is if you're entering a calculation that involves a trig ratio, you need to convert to radians. So change 60 degrees into radians by multiplying by the conversion factor pi over 180. And so this would be, and make sure that that conversion happens inside the trig function. And so that would be the calculation you could enter as your solution. All right, so expect to see a question like this on your assessments. All right, the next couple types of questions you're going to see are applying a rule that again applies to non-right triangles. Okay, it will work for right triangles, but if you do have a right triangle, trig ratios are more efficient. Okay, but this is called the law of sines. And the law of sines is a relationship that says for any given triangle, if you take the ratio of its side to the sine of the angle opposite that side, again, where the lowercase letter is the side opposite the angle with the same uppercase letter, this is consistent for all three sides of this triangle. So the ratio A to the sine of A, or side A to the sine of A, is going to be the same as the ratio of side B to the sine of the angle opposite that, capital B, and that's the same as the ratio of C to the sine of C. So this is what law of sines refers to. Now, you're not going to do all three calculations here. You're simply going to take whatever two of them you need. One of them will have your unknown, and then the other one, the other side of the equation, will have your two knowns, which I will refer to as your the known ratios. So when you look at this, if you're solving for an unknown side length, like we are right here, and the two congruence patterns that work for law of sines are the two with two angles. So ASA and AAS work for law of sines. So when you see that, if you're taking the law of sines and solving for an unknown side length, you'll use this ratio. Now, if you are solving for an unknown angle, which we'll do tomorrow when we look at the pattern SSA, which is not a congruence pattern, but it is a pattern for law of sines, we'll take a look at that. And if in that scenario, if you're solving for an unknown angle first, what you could do is you could flip each of these ratios as well. So we could have also said that the ratio of sine of A to the side opposite that angle is the same for all of these. So sine of B over side B, and that's equal to sine of C over side C. So these all depend on what your unknown is, and I encourage you to put whatever your unknown is in the top left of a fraction or of the equation when you're solving. All right, so I'm going to walk you through the steps on this problem here. So if you're given two angles, either ASA or AAS, and you're asked to find all the remaining pieces of information about the triangle, you're given two angles and a side. Easiest thing to find first is going to be the missing angle. And you can find that by using triangle sum. So here, if we just kind of sketch the triangle that's being illustrated, triangle ABC, where angle A is given as 39 degrees, C is 72 degrees, side B is 22. Remember, the lowercase letter is the side length opposite the angle, the same capital letter. So first, when you see this, you have two angles and the included side. So this is the ASA pattern, which indicates we're going to use law of sines. Find the missing angle first. So the missing angle can be found by just taking triangle sum. If we subtract 180 minus the two given angles, so 39 minus 72, this will give us our solution. Again, we can enter our answer as a calculation here, or if we do the calculation, so 180 minus 39 minus 72, we get our angle measure to be 69 degrees. Okay, so either of these would be acceptable calculations. All right, so once you find that third angle, that last angle, what you can now do is use law of sines to find the two remaining sides. I will often abbreviate law of sines just L of S to kind of represent that when I abbreviate it, sketch it out. But we're going to use the law of sines to find these missing sides. And you can do it in either order. Just the fact that it asks for A first, I'm just going to solve for A. So if I take my unknown side A, which is opposite angle A, I set up my law of sines. A over the sine of the angle opposite that, which is 39 degrees, is equal to my known ratio. Now, after I find B and label it 69 degrees, this is now my known ratio, the B's, right? Because I know both side B and angle B. Once you have the side and angle known, that becomes sort of the ratio you can compare to. And so here, since A is a side length, I'm going to begin with the side B, 22, over the sine of the angle opposite 22, which we see was 69 degrees. So this is my setup. To calculate this, I can now isolate A by multiplying both sides by the sine of 39. And so there is my solution. And again, if I type that in, I get 22 over the sine of 69 degrees, all times the sine of 39 degrees, giving me my answer of 14.83. Now, it is possible that you could enter this as a calculation directly in your MyOpenMath, right? So we talked about what that involves, and it involves taking any trig ratios, so sine of 39, and converting them into radians. So we'd need to multiply that by the conversion factor pi over 180, and the same thing in the denominator, sine of 69 times pi over 180. So if we entered this as well, that would be an acceptable form of our answer. Okay, to find C, we do the same thing. So we take our unknown, C is opposite angle C, so C over the sine of that angle, opposite it, 72 degrees, is equal to, the known ratio doesn't change, so I can keep that same known ratio, which allows me to solve this by multiplying both sides by the sine of 72, and that isolates my C. And notice the nice thing about this Desmos calculator in TI-89 works as well, because you see the displayed values. All you need to do to recalculate this is change this 39 to a 72, because the conversion or the known ratio stayed the same, and you get 22.41 as your answer. Again, if you wanted to, you can convert it into or you can enter it as a calculation by converting it into radians and entering it directly on your MyOpenMath. But the calculator winds up being a really easy way to approach it. So I would, again, just probably recommend doing it on the calculator. All right, so on your quizzes and tests, you're going to get one of this, either this form, the ASA pattern, or you're going to get the form on the next slide, which is AAS, and that's solved the exact same way. So I'm going to copy the steps here. And I want you to try this one here on your own, please. Okay. Can you find all three missing pieces of information for this triangle, okay, based on the law of sines? All right. So if we take this, I'll sketch my triangle here really quickly. Call it triangle ABC. The knowns for me are 42 degrees A, C is 67 degrees, and A, which is the side opposite angle A, is 12. So here my pattern, I have two angles once again, and a side. The side is not included between those two angles, and the two angles will always indicate law of sines. So the easiest thing to do is find B first. I can do that by using triangle sum. 180 minus the given angles, 42 and 67. And when I do that, I get my solution. (180 minus 42 minus 67) leaves 71 degrees. So there's my first answer. And then I can either find B or C. Since B is written first, I'm going to go ahead and solve for that. I'll use the law of sines in looking at this example here. The law of sines is the ratio of my unknown over the sine of the angle opposite it, opposite. So here's my unknown. Opposite B is 71 degrees. Set that equal to my known ratio. So when I look at the given information, there's only one set of values that I have both a side and angle for. That's my A's. So the A's are the known ratio here. So since I started with a side on top, I'll put my side 12 over the sine of the angle opposite at 42 degrees. And then just calculate. So multiply both sides by the sine of 71 degrees. And there is my solution for B. And I can type that in 12 over sine of 42, again, as long as you're in degree mode, times the sine of 71. Gives me my answer of 16.96. Or if I entered this online, or on MyOpenMath, sine of 71 times pi over 180, I could enter that calculation directly in over sine of 42 times pi over 180, again converting from degrees to radians. And so I could have entered this as my calculation. I'm not going to do this on the last one, but I'll do it on the first just to review that process. And the reason is because when I do set up and solve for my other side, C, I can use this same type of idea. The side C over the sine of the angle opposite it, which was 67 degrees, is equal to my known ratio, still going to stay the same, 12 over the sine of 42. Therefore, to isolate and solve for C, I multiply both sides by the sine of 67. And notice the only change I need to make here is change my 71 to a 67. I get 16.51 as my side length, and there is my final answer. Okay. So that is using the law of sines in the patterns of ASA and AAS to find all the remaining pieces of an unknown non-right triangle. The other instance that I want to talk about today is going to be the law of cosines. So again, if you skip 3 slides, you'll come to the one that says law of cosines SSS, or side, side, side. The law of cosines works with 2 congruence pattern scenarios, and it's the 2 that include 2 sides. So SSS or SAS are the indicators that you're going to use law of cosines. We're not going to derive it, but I'm going to talk about the formula really quickly. You'll be provided the law of sines and law of cosine formula, so you don't have to memorize these. Okay? But the form that you're going to get them in is just one set of equations. So for the law of cosines, it's going to look like this. C squared equals A squared plus B squared. So it's based off of the Pythagorean theorem, okay, with an adjustment of side C squared is equal to, so this is a non-right triangle, A squared plus B squared with the adjustment of minus the product of those 2 sides times the cosine of the angle opposite this original side. Okay, so capital C. One of these 2 elements here or here is going to be your unknown. Okay, if it's the pattern of SSS where you don't know any angles, you're going to solve law of cosines for capital C. That's going to be your unknown. Okay, if it's one where you have the pattern of SAS, then the unknown side that you're going to find is going to be this lowercase c, and that's the side that's opposite whatever the angle is that they gave you. Okay, so again, you'll see these when we go through the patterns. Today we're just going to look at the SSS pattern. Now, there are 2 variations of this, again, depending on what pieces of information are provided for you. If angle A or side A is your unknown, then you'll put that by itself, and it's equal to the sum of the squares of the other 2 sides, minus twice the product of those 2 sides, B and C, all times the cosine of the angle opposite A. And again, either angle A or side A would be your unknown in this problem. Or if B's are your unknowns, then you take the sum of the squares of the other 2 sides, A squared plus C squared, minus twice the product of those 2 sides, all times the cosine of the angle opposite this side B, which is angle B. And once again, either angle B or side B would be your unknown in that form. But you're going to be given the top form. I'll write it on the board on quiz and test day. So let's take a look at what's going to be, or how this problem is going to be solved here. The first thing that you're going to do, or actually let's take a triangle. So here's A, B, C. So in this problem, when you're given a pattern of SSS, so we have side A is 39, opposite angle A, side B is 36, opposite angle B, and side C is 40. Now, without going into a lot of details about this, when you are calculating angles, unknown angles using inverse trig ratios, and there is something somewhat unique about inverse sine versus inverse cosine. Inverse cosine is going to give you values from 0 to 180 degrees. And so when you take an inverse cosine, you will get all possible angle measures that could exist in a triangle, okay, from 0 to 180 degrees. But in an inverse sine calculation, you're going to get values from negative 90 degrees to positive 90 degrees. What that means is if you take an inverse sine of a ratio and you get an acute angle, it means that there's another obtuse angle that has that same sine ratio. Again, we'll talk about why that's the case or how it's the case when we go back over unit circles, which we'll try to do when there's time. Okay, but for right now, just need to know it's if you try to use the inverse sine to find an obtuse angle, there's extra work involved in it. So if you're given a problem like this, where you have all three sides and you need to find an angle, or all of the angles, find the largest angle first. Okay? Because using law of cosines, you're going to get any obtuse angles. So when I look at this triangle right here, what's the only angle that could even possibly be obtuse? Remember the inequalities? The largest angle is opposite the longest side. So there's only one possible angle that could even be obtuse, and that's angle C, right? So start with that. So when you're going through your steps here, and I'll call L of C for law of cosine, use law of cosines to find one angle. And I would recommend just find the largest angle first. And that way, if there is a calculation that is obtuse, you'll get it. And if it's not, then you know that no angle is obtuse. Right? So if I use this law of cosines calculation to find here my largest angle C, so these are going to be the pieces that I use. So that means my known side, 40, will be on the left side of the equation, equals the sum of the squares of the other two sides, 36 squared plus 39 squared, minus twice the product of those two sides, all times the cosine of the angle opposite my original side, 40. Okay, so this allows me to solve for C. Okay, this calculation is messed up a lot by students. Okay, so take your time on it, have sort of a structure, a way that you approach it. And so what I would recommend, and you'll see me write it down here before I even calculate it, is we're going to undo everything first. So I need to subtract these two values first. So I'm going to get 40 squared, I'm going to subtract 36 squared, and I'm going to subtract 39 squared from both sides. Okay, so both of these get moved over. Now that leaves everything equal to this quantity. And so to isolate my variable, I'm now going to divide everything by all three of these factors. And again, notice I'm leaving them as factors. So -2, 36, and 39. So all of this cancels, and that leaves my cosine C. So by rewriting it in that form before I start calculating it, I get a chance to see how this calculation is going to look. So when I do this calculation, I'm going to put grouping symbols because I'll have a fraction. And I have 40 squared minus 36 squared minus 39 squared in the numerator. And then I'm going to divide that by everything in the denominator. Notice I keep the sign, -2, 36, and 39. Okay, and this gives me my decimal value. So I have 0.4334 being the ratio, the cosine ratio of angle C. And so that's what this means, right? Cosine of C is 0.4334. That means that if I want to solve for C, I can do it by taking the inverse of that cosine ratio. So the inverse cosine of that ratio gives me my answer for angle C. Now, in order for me to do that as a calculation on this Desmos calculator, I want to pull up this exact value. I don't want to use approximations. If you use approximations, you might be off by enough decimals where it won't accept the tolerance level. So if I go back into my first line here and I assign it a variable, it doesn't matter what you assign it. So let's call it m. So if I say that this is equal to m, what I can do on my next line is I can take the inverse cosine of that quantity that I assigned m, and it gives me my angle. So my angle is 64.32 degrees. So that's C. Now, once you find that measure, so I found my first angle, you can either repeat this step and do this again. So if we repeat step number 1 for a different pair of angles or a different angle, either A or B, and solve that, that's one way that we can approach this. A better way, because it's a simpler calculation, is going to be to use law of sines for the next angle. So if we use law of sines, L of S, to find that second angle, okay, that's how I'm going to set this up. So again, come back up here, and my angle C was 64.32. But again, when I use this as a measure, I have to use the exact value. And now I can see from that being circled. Those are my known ratios. So if I want to find A next, I can use the law of sines, which I will take my unknown and put it on top. So sine of A over the side opposite A, which is 39, equals my known ratio are my C's. Since I'm starting with the angles on top, I'm going to take the sine of 64.32 over the side opposite that, which is 40. And so I can solve this by multiplying both sides by 39. That gets my sine of A alone. And now I do my calculation. So as you watch how I do this calculation here, I need to refer back to this original angle. So I'm going to go in front of this calculation, and I'm going to call it C, because that's my angle C. So if I look at this calculation here, I'm now going to take the sine of C. I'm going to divide that all by 40, and then I'm going to multiply that result by 39. And that gives me the ratio 0.8787. Okay, and so that means that for angle A, the sine ratio is 0.8787. And lastly, I can find angle A by taking the inverse sine of that ratio. And just like I did before, I need to call up this exact number. So I need to give it another variable. I'm just going to call it n this time. But you can call it any letter. Pick something from the middle of the alphabet. And when I take the inverse sine of that n, I get my other angle measure, which is 61.48. And that would be my angle A. So if I go back here, type in 61.48, I get my second angle. And again, if I want to enter it here, there's my measures. So that brings me to the final angle, and the way to find the final angle is to use triangle sum to find that last angle measure. And when you do this, this is the one case where, because you want the total sum of angles to equal 180, you'll use the approximate values here. So if we just type in 180 minus the 61.48 minus 64.32, we'll get our calculated value here, which if we do that calculation, So 180 minus 61.48. So again, don't use the exact values here because sometimes when you use exact values, they don't quite match up to a total of 180 degrees. You get 54.2 for this last angle. And so that would be your final part to this question. Now, I already wrote the law of cosines down for you last time. But remember, the law of cosines is based on this sort of Pythagorean theorem, c squared equals a squared plus b squared, with the adjustment minus twice the product of those other two sides, a and b, times the cosine of the angle opposite this side, which is angle c. So this is the formula that I will give to you. You don't have to memorize this. We'll write it up on the board if you are, when you're taking a quiz or a test for this. Okay, but this is the only version I'm going to give you. It won't necessarily be the C's that are your unknowns. It could be the A's, could be the B's, but this is the sort of the relative relationship for those. All right. So I want you to see what can you recall or what process can you use that's similar to what we did yesterday using this law of cosines to find this missing information, and I will put I'll put the steps here. Okay, the first thing you'll do is you'll look to solve for the missing angle in this case. Or sorry, for this you're given the angle, you're going to solve for the missing side, the side that's opposite the given angle, and then from there you can use law of sines or law of cosines to find the remaining pieces. So step one, use the law of cosine to find the third side. And then again, I would recommend that you use law of sines, but you can either use law of sines or law of cosine to find a second angle. And then I would recommend using triangle sum to find the third side, or the third angle. All right. So first thing let's do is use the law of cosines to find the third side. So if we label what we have here, I'll call it triangle A, B, and C. Side A is 44, so that's opposite the angle A. Angle B is 41 degrees, and side C, which is opposite angle C, is 65. So here's the information that's provided. You can see you have this S with an A in between, so SAS pattern. The SAS and SSS pattern tell you you're using law of cosines. And so if we set this up, what we're going to do is we're going to take again, the unknown is either the very first or the very last piece of information. So for the SAS pattern, the unknown is the side. Okay, so if we take our unknown side, which is b squared, equals the sum of the squares of the other two sides, minus twice the product of those two sides, times the cosine of the angle between those two sides. Okay, and so this is just one single calculation, right? So when we go into our calculator, and I'm going to use the Desmos one, first time since we're dealing with trig ratios, always make sure go into your settings, this little wrench tool, and change your change from radians to degrees if you're opening it up for the first time. And then you can just you can type this whole thing, 44 squared plus 65 squared minus 2 times 44 times 65 times the cosine of 41. Now, this gives you your whole value. This is the b squared value. Okay? Now, you could have, before you even started this, you could have done a square root around the whole thing. So again, if I took this, I'm going to go in front, put parentheses around it. So notice I just put parentheses around that whole calculation. And then in front I can type, I guess it's not going to allow me to do that. Let me try one more thing. If I highlight this whole thing and hit square root, nope, it's not going to allow me. So I'm going to go ahead and just leave this calculation right here. and I'm going to call it some variable. So I'm going to say m equals, so I can then take the square root of that separately. So if I kind of set this whole thing equal to m, and then I take the square root, that's going to give me my b value to be 42.94. And so that would be the first measure that I'm looking at. Now, when I go in and label what I have, so if I'm thinking of this is 42.94, okay, I am going to be using that in my future calculations, because now I will have a known ratio. My known ratio is going to be the b's. And so once again, I'm going to go back into my calculator, and I'm going to set that equal to my lowercase b. So that's my side b. So I can refer to that anytime in my future calculations here. Now, when we move to the second step, you can choose one or the other. The law of sines is an easier calculation, in my opinion. Okay, and so here, if we're going to find our second angle, anytime you're unknown on the law of sines, you're going to put that unknown in the numerator. So let's say I want to find angle A first. So if I start with that in the numerator of my fraction, sine of A over the side opposite it, which is 44, is equal to my known ratio, the sine of the given angle, 41 degrees, over the side I just found. Now, I can write 42.94, but because I've already assigned this, the letter B in my calculation, I'm just going to put B right here. So it's just easier for me to see what my calculation is. And so now when I multiply by 44 to get sine of A alone, I can now move to my calculation is the sine of 41 divided by B. B pulls up that exact value of my side B. And then I'm multiplying this by 44. And so this gives me my sine ratio for angle A, so 0.6722. Now, even though I wrote this down as 0.6722, and when I rewrite my inverse sine of that ratio, I still only stopped at those 4 decimal places. When I do my calculation, I have to use the exact value. So I'm going to go back in here, and I'm going to give it another variable name. Again, somewhere in the middle of the alphabet is easiest. So I'm going to refer to this as n. Right, so this is now my n. So if I just take the inverse sine of n down here, so sine to the power of -1 is the inverse sine of that whole decimal ratio that I have representing n. I get 42.24 for angle A. And so there's my second angle. And then that leaves my final step. My final step here is to use triangle sum to calculate the third side, or the third angle. And again, when you're using triangle sum to get that last angle, you want the total sum of all your angles to equal 180. So this is the time, this is really the only time we'll use the approximate values for these. So if I took 180 minus the given 41 minus the angle that we just found, 42.24, that's going to give me my angle C. And if I do calculate that, 180 minus 41 minus 42.24, again, I'm not using the exact number here because I don't want my rounding to give me different values, but I get 96.76 for my final answer, which you can either write in the calculated form, or as that rounded decimal. Okay, and so that would be the measurements for this. So you can see that these are like more calculations involved in them, but it is, if you know the law of sines and law of cosines, you're going to use both for these law of cosine problems. But it's just a matter of managing your calculations and making sure you're in the correct mode. Okay? All right. Any questions on that? All right, so we're going to go backwards here for a moment and go to the very first slide that introduces the pattern of SSA. Remember, this is not a congruence pattern, but it is a pattern that indicates we're going to use law of sines. But the one thing with the SSA pattern is that there's not just one scenario. It's one of two different things. Okay? And so if you have this case where, oops, bless you. All right, so let's say these are the pieces of information given. You're given an angle, and you're given two sides, right? So it's this pattern of SSA, where the angle's not between the two. Okay? Depending on which side is longer will determine whether you have two possible triangles or one possible triangle. Okay? So if I use, let's say, for example, I use these two measures. So in this example, the side that's given opposite the known angle is the smaller of the two sides, versus here if I switch those, right, and now I have the longer of the two sides is opposite that given angle. And so this is how you can, or this is what you look for to determine whether you have two or one solution for these. Okay, so if you're looking at this and the information that you have is two sides and the non-included angle, two sides and the non-included angle. Okay, if the given side, or sorry, if the side opposite the given angle is the shorter of the two, then there's two possible triangles. Okay, so if you look at this, what we see right here in red is one possible triangle. If you think of this side of 10 kind of hinging at this intersection point, is it possible for another triangle to exist that also has a side of 10, then 12, and then that given angle? Yeah. So do you see how this blue triangle here is the second version of this? Okay, so that's the second triangle. The outer one is the first. Okay, however, if you take, and the longer side, if the side opposite the given angle is the longer of the two, then there's only one triangle. And because imagine if you hinged this side right here and tried to rotate it around, could you create an angle or another side here that's 12? No, because this is an obtuse angle, and the side opposite the obtuse angle has to be the longest side in your triangle, so there's no way a side of 12 could be in this location. So if the given, if you take the side opposite the given angle and it's the longer of the two, there's only one triangle. If it's the shorter of the two, then there's two possible triangles. Okay, so the first thing I want you to do, and this is all that you're going to be, or this is what you will be tested on about SSA pattern, is can you determine whether it's one or two solutions based on the SSA pattern. So I want you to answer these two questions here and see which one is two solutions, which one is one solution. Right, when I sketch these out, I will always put them in this same kind of orientation like I did the example that I drew up here. Okay, I will draw them out with the given angle. So if I see my given angle, I have one angle and two sides. The sides are not, or the sides do not include the angle. I'm going to put my angle down here. So my B is going to be right here, 26 degrees. And so now I have B to C and then C to A. Okay, so I know my BC is right here, so I'll say BC is 20. CA is longer than that. Okay, so I'm going to exaggeratedly make CA longer, because if I see that that's longer, so here's point A, then even visually I can see right here, is it possible for me to hinge this side and redraw it over in this direction and form this isosceles triangle right here? The missing part or the difference part is an isosceles triangle. No, that's not the length of CA. So what I can see right here in this example is that when my longer side is opposite the given angle, I have only one possible solution. So that's the only triangle that exists there. Okay? But if I look at the other instance, So again, I have angle B with two sides. My angle B is 39 degrees. BC and then CA, so I know that C has to be this point right here, so that's 35. And then CA is a smaller side than 35. It's 21. So what I can see is I can sketch that so it's exaggeratedly shorter. And when I do, I can then see if I hinge this back, can I create a second triangle right here that is also a length of 21? Yeah. And so here there's two solutions for that set of information. Okay, so it all depends on whether the side opposite the given angle is shorter or longer. If it's shorter, there's two possible triangles. If it's longer, then there's one. Okay. Right. So what we're going to do here for these last two slides and calculations is we're going to solve for these triangles. Now, obviously, the one where there's one solution is going to be the easier one to solve. You just follow the same rules that we've done using law of sines. Again, SSA pattern indicates the law of sines. But if you have the example where there's two solutions, it becomes a slightly harder problem, and I'll go through that in just a moment. Okay, but let's start with the easier form first. Okay, what happens if you only have one possible solution here? Right. So here, if side A is larger than side C, right, with those labels that are right there, if the side opposite the given angle is greater than the other side, you're just going to use law of sines. To find the angle that's opposite side C. So we'll find angle C. And then once you find that, you can use triangle sum to find the other angle. And then you can use law of sines once again now to find the remaining side. All right, so I'm going to walk you through this, and then when we do the next one, I'll have you sort of try on your own. So let's look at this scenario. All right, so first case is, and you're not going to specifically be told that this is a single triangle. So if we take our angle B is 38 degrees, we have BC and CA, so we know that we're going to meet at C. So BC is 18, and then CA is 19. So that is longer than the original. So that tells you you have one solution. Okay, so that's the first thing. You'll need to determine this on your own for your homework anyway. And so what we now have is we have one known ratio. The B's are our known ratio. So the other piece of information that we can solve for first is going to be our angle A, since we already have side A. So we can set up our law of sines. Remember, law of sines is sine of A over A equals sine of B over B equals sine of C over C. And you can flip these either way. I'm putting it this way because the first piece of information that we're finding is our unknown angle A. So if we take sine of A over the side opposite that, 18, is equal to our known ratio. Since we started with angles on top, we're going to start with the angle sine of 38 over the known ratio of the side opposite that is 19. And so when we do our calculation here, we're going to multiply both sides by 18. That gives you sine of A. Notice, if we take sine of 38 divided by 19 times 18, here's our decimal. This is our ratio for the sine of A, which means if we want to calculate A, we're going to take the inverse of that. And in order to use the calculator for this, I want to call this some variable. I'm going to call it some constant m. And so if I then take the inverse sine of m, I'm going to get my angle, which is 35.68. Now notice this one doesn't ask me to solve for C, right? But in order to find my answer, I do need to know what C is. So my measure of angle C is simply going to be the triangle sum. 180 minus the given angle 38 minus this angle A. And so once again, I'm just going to call this A. I'll go ahead and capitalize it to represent the angle. But angle A is 35.68. And you do want to use the exact calculation for this. You only use approximations when you're submitting your answers, but for this, it's part of the calculation. So when we set this up, we want to take 180 minus the known angle, 38 minus A. And so I get angle C is equal to 106.32. And once again, because I'm going to refer to this in a calculation, I'm going to go ahead and call this angle C, or capital C, in my calculator. The final step is to find my missing side. The last side here left is lowercase c. And so to use that, I'm going to take the same law of sines, but now I flip it because my unknown is c over the sine of c. That's equal to, and I can use either of these, but it's the b's that I actually have as my known ratio. So if I use that calculation here, so if I get c over the sine of c, which I've already assigned that in my calculator, so I'll leave it written as c, is equal to my known ratio. Now I'm using the side on top, so I'll put 19 on top over the sine of 38. And so if I multiply both sides by the sine of c, I get my value. So 19 divided by the sine of 38. Oops. And I'll move this here. All times the sine of c. And I get that answer of 29.62 for my last side length. All right. So this is the process that you will use for your homework questions given SSA. You're not going to be quizzed or tested on this, but it will be on your homework. And what I want you to do is I want you to try that entire process right here with this question. Okay? Now, keep in mind that you're only going to find the first example of this, and then I'll show you how you can find the second example, and that'll be the end of our notes. Okay? So, but you should be able to find the first one by following what we just did. All right, so let's take a look at this first problem here. Okay, so when you're looking at what you have, angle B is 27 degrees, BC is 34, and CA is 16. So the first thing that you would do here is you recognize your pattern is SSA. So SSA means law of sines, and there can be either one or two. Since the side opposite the given angle is the shorter of the two, that means that there's two triangles. So that's the very first thing. You need to figure out that you are anticipating two triangles here. So what we can do is we can go through these steps just like what we did in the previous problem to find the first triangle. So we're going to take, here's our known ratio. So the piece of information we can find first is angle A. And so if we set this up using law of sines, the sine of A over the side opposite it, 34, is equal to our known ratio, angle on top, so sine of 27 over the side opposite it, 16. And we solve. Multiply both sides by 34, and that gives us our sine ratio. So if I go ahead and do the calculations for this, okay, so I get sine of 27, divide that by 16, and then multiply by 34. So that is my ratio here, 0.9647. But because I want to find the inverse, or because I want to find the actual angle A, I'm going to take the inverse of this. And so since I'm using a full calculation here, I'll give it some variable. It can be whatever you want. But if I take the inverse sine of M, this will give me my angle measure. So I get A to be 74.74. Okay, so there's my first angle, and I'm gonna go up here and I'm gonna label that 74.74. Oops. So there's my label. All right, move to the next piece of information, which is I can now use triangle sum to find C. So I am going to call this angle A. And my angle C is going to be 180 minus my given angle of 27 minus the angle I just calculated. And so what I see up here is this is going to be 78.26 for my angle measure. Once I have that angle, I can now solve for the side opposite it, which is lowercase c using law of sines again. C over the sine of the angle opposite. I'm going to call it C. So I'm going to go down here again, use capital C to label my angle. So that's the angle I'm referring to, 78.26, is equal to my known ratio. Now my sides are on top of my proportion, so 16 over the angle, sine of the angle opposite it, 27 degrees. So if I multiply both sides by the sine of C, I get my C value here to be 16 divided by sine of 27 all times the sine of C. And again, I'm just going to label it as capital C to represent that. And I get 34.51 as my side C. All right. Now, I am going to kind of label that here too, just so you can see where everything's represented. All right, now here's the issue, or here's the thing. I have two triangles here. So what that means is if I were to hinge AC at point C and rotate it back this way, where these are the same length right here, it creates this second triangle. Okay, this second triangle is this pink shaded triangle where I'm going to call this A2. This is my new A point. Up here, I'm going to refer to this as C2 just to represent that it's the new angle C in my second triangle. Okay, and so what I can do to solve this triangle right here is I can go back and I can use all the same information to solve for this. Oops. So let's say we come back here. If I know that this angle, A, is 74.74, and this is an isosceles triangle, what does this other angle here have to be? The base angles of an isosceles triangle are the same, right? So that's 74.74, which means what's this new angle in here? What's my new angle A going to be? 180 minus the original angle A. And so that's going to give you your new angle A. Okay, so I'm going to call this one lowercase a. I know like that generally represents the side, but however you want to designate it. But if I take 180 minus A, what I see here is my new angle A is going to be 105.26. Okay, so there's my second answer. So these would be my two answers. Again, you can use a calculation if you want. And then basically what you're going to do is you're going to redo this last calculation here for C. So I'm going to go ahead and just call this, I'll call this a different letter. I'll use E for this one. So if I say E over the sine of the angle opposite it, which is this new angle here, and this is the angle, and I'm going to call it angle E. So let's refer to this as angle E. In order to find this angle, Angle E is going to be 180 minus my 27 minus this new angle A, right? Minus the 105.26. So what I need to do first is to find, I need to find that new angle measure that represents this angle right here. And so if I take 180 minus the known angle 27 minus this angle that I just calculated here, which I called lowercase a in my calculator. And so I get 47.74. And so that is my new angle. So when I set up my ratios, E over the sine of the angle opposite it, 47.74, is equal to my known ratio is still going to be the same, 16 over the sine of 27. And so if I do the same set of calculations, multiply both sides by the sine of 47.74, and that's going to give me my new answer. So what I'm going to do is, this is my new angle. I called it E here. So I'll say E, capital E is equal to. And so when I set up my final calculation, 16 over the sine of 27 times the sine of this angle up here that I called capital E. And it gives me my final answer, which is 26.08. And that would be the second part to this question. All right. So you could